All righty. I think we are live. All right. Good to see everybody. Today, on our 6th episode, we will be talking about all things TEEs with the great folks from Turnkey. So, before we get into that, quick disclaimer. So, this podcast is for informational purposes only. Nothing said on how things work should be interpreted as an offer to buy or sell securities, financial advice, legal advice, in this case, probably security and cryptography advice, or as an opinion of employers at which our guests work. Lastly, our guests and I may hold positions in the companies or projects discussed. In fact, we all probably do. So with that out of the way, for those listening for the first time, How Things Work is basically a podcast geared towards a technical audience on basically where a lot of other podcasts stop and say this is too technical, like people are going to lose us. That's where we try to start and go as deep as we can onto different technical concepts related to building blockchains and interacting with blockchains. With that, let's get into it. So today we have 3 guests joining us from Turnkey. I will let them introduce themselves and then introduce Turnkey, and we can get right into it. Because I knew Arnaud first when we worked together at Coinbase a number of years ago, we'll kick it over to him first.
All right, cool. Yeah, thanks for having us. So my name is Arnaud. I work at Turnkey. Obviously, I'm an engineer here. Prior to Turnkey, I worked at Coinbase building Coinbase custody, and that became Coinbase Prime. So my background is in key management there. I spent about 4 years building this, and then joined Turnkey with Jack and Zeke, who are here. Today, what I do at Turnkey is mostly backend and sort of like at the frontier of backend and infrastructure. I'll keep it short, and then we can talk more about kind of the technicals and the different parts of Turnkey and architecture and all that good stuff after. Jack, do you want to go next?
Sure. Hey, everyone. I'm Jack. Been at Turnkey for a while. I'm the co-founder or CTO at Turnkey. Prior to Turnkey, was at Polychain for a number of years, doing kind of internal custody work and a lot of staking operations work at Polychain, some technical diligence. And then before that, was working at Coinbase for a number of years, originally on the inference security team, and then transitioned over to be working at Coinbase custody. So Arnaud and I first connected at Coinbase custody, just pretty much getting it off the ground. So I was one of the first people working on it and kind of helped design the cold storage system that it was based on, and then kind of got the first customers in and actually did my first staking work in Coinbase custody for the Tezos blockchain. If you guys haven't remember that, one of the first proof of stake blockchains that was live at the time. Excited to dive in.
Awesome.
My name is Zeke. I've been at early Turnkey, joined the same day as Arnaud, pre-seed. Before Turnkey, I was at Parity, and actually before that, I knew Jack. I met him while I was in school because he was working at Polychain. My friend worked at the front desk. While I was in school, started doing open source kind of contributions to the Parity Polkadot code base. Started there before they were, when it was chaos. And I think, Patrick, I was actually on some calls with you. I don't know if you remember, but when you guys were integrating Polkadot, and I moved up from doing integrations to mainly focused on scaling the proof of stake system. And then at Turnkey, I was mainly focused on building out the operating system for the enclaves and kind of building out all the support for us to build apps in the enclaves as well.
Got it. Yeah, very possible. Yeah, for the listeners at home, Polkadot was one of the first things I worked on when I was at Coinbase integrating stuff, and I met a lot of great people over there. I mean, one of the fun parts of, I'm sure you guys feel the same way of like working at Turnkey or was working at Coinbase was you get to talk to so many different folks, like great projects that are really trying to push the envelope of what's possible. But the invariable problem that has come up for years now is like, users got to have keys. So, where those keys go and how those keys are safely managed, right? Like, I think people say, well, not your keys, not your crypto, right? But assuming you don't want to store your own keys, what do? And to me, that's a lot of where Turnkey has had a lot of success lately. So maybe you guys want to start off also kind of what is Turnkey? Clearly you guys have quite impressive backgrounds working on the problem space. But I think that'd be a good place to start, and we can get right into it. Zeke, I think you were going to say something. I don't know if you want to comment.
Oh, just a really quick anecdote, because I was working at integration. Like one of the primary integrations that I was like plopped into right when I first started was Coinbase, and I saw all these integrators across the spectrum who were trying to integrate with Polkadot. But I remember when Jack initially pitched the idea for Turnkey to me, I was like, oh, this must exist already. It just seemed like such an obvious thing to have key management by APIs that was highly composable, low-level primitives. And yeah, so that's kind of like how I ended up here. So I was like, this is just such an obvious thing in such like a massive part of the space that's underserviced.
Zeke, you kind of gave the pitch there. You want to
So I guess like for a really high level, Turnkey, we handle like user wallets for blockchain. But I think you can back up even more and just say we're an authorization layer. So what is handling keys? There is making sure these secrets are never exfiltrated, like no one can see them. But also importantly, and probably like the biggest challenge, is making sure the proper authorization for using those secrets. And I think of it as like anyone who wants to interact with the blockchain, especially when you talk about organizations, not just individuals. Like I can't have an organization just like share a MetaMask wallet. Like that's like not reasonable. You need some sort of way to programmatically interact with a blockchain, or I think, kind of, we're just going to see a lot of other things that look like blockchains that are cryptographically authorized. And this is like the intermediary layer to make sure that authorization can be very expressive and programmable.
Well, I mean, FTX just stored the key in Gmail, right? So you can't just share a MetaMask wallet, but sorry.
Sure. Gmail. I mean, you hear crazy stories about people in Excel sheets, and you just have Python scripts that, are just using those. And like, honestly, like maybe for some very, frontier use cases where it's not supported, like the cryptography is not supported or something, like you just need to do that. And, something like Alameda or these things you hear about, like, maybe they have like some good reason to have these really bad practices because they just need to be so quick. But I think we should be in a space
or you don't have a good reason.
Yeah, or you don't have
I was going to say no good reason. No good reason.
This is not security advice. Yeah, usually no good reason. But
basically, like I think we are moving towards a world where this is going to be there is no good reason, right? And that's kind of where Turnkey sits. And I think that the other thing to think about is like all access to a blockchain like happens through some private key infrastructure, whether that's your ledger, your MetaMask, or I think a lot more we're seeing embedded wallets, and things are getting much more automated. But I think this is like an absolutely massive space that probably isn't like the sexiest. We're not building some super high speed like order book or whatever, but in order for you to use that, right, like you're going to have secrets stored somewhere, and you're probably going to want authorization access for them. And I think it's kind of cringe to say, like this is like the most cringe thing to say of like how are people like going to, how is the world going to use blockchain? But I think kind of these pieces of getting private key infrastructure right, or servicing areas of it very well, are like is a massive space, and is truly key to seeing like these types of more trustless technologies, these more verifiable technologies take off. And I think that's only going to become more true as we see like more of like the world take shape, and we're in more like adversarial environments for computers and stuff, as we're, nation states go to war and blah, blah. But like, I can go on a crazy rant, but I think you get the idea.
Yeah, I mean, I think the point you made around like just the adoption of more like solutions that require like cryptographic authorization is like a really interesting trend that, I mean, certainly what you guys are working on now is, pretty purpose built for blockchain stuff, but like it definitely doesn't need to always be geared for blockchain type applications. I always think about it too. It's like, finally, we have passkeys of some variety that let you do kind of more natural, like cryptographic authentication. But you can imagine, like, why do you even have passwords on all these things? Like, I should just have a public key that I can then just use in some sort of registry where I can change the public key that I'm using to sign in. Like, wow, that'd be so nice. If only. But so Great to hear. I don't know if anyone else wants to add anything to that description.
Yeah, I'll add something real quick, because I think one of the main thing that we were thinking about when we created Turnkey was creating this like infrastructure primitive, as opposed to creating a wallet level or transaction level primitive, because like everybody here knows really well the pressure and the sort of toil that comes from asset addition. Every time you want to support a new type of asset, every time you want to support a new type of transaction, every time you want to support a new type of ecosystem, even if the underlying cryptographic primitive for signing is the same, you still need to add these things. And so at Coinbase Custody, Coinbase Prime, and I'm sure in other sort of custodians, the infrastructure and the teams that manage keys have to deal with that day in, day out. And so at Turnkey, from day zero, we were saying like, okay, let's not ever go with, asset level, transaction level things. Let's go lower level curve based primitives.
Mm-hmm.
And so that means that, yes, it can be used to build up to something like Bitcoin, something like Ethereum, something like Cosmos, something like Solana. But if you have ED25519 support, you can also build up to just like use that as a PGP signature, right? Like if you, or if you have P256 support, you can also extend that to use a Turnkey key as a fake HSM or as a cloud passkey or something like that, right? So it really is built to be that sort of primitive that lets you exchange an underlying key that you don't want to leak out to anybody, that you want to pin to a set of authenticators and a set of users that can use that key, and then you can do administrative actions on the signers for or the authorized parties that can use that key, and that can rotate a lot easier than if you were to rotate the underlying key.
Sure.
So I think that's the piece that I think a lot of people overlook, is the sort of technical foundation that led us to believe, okay, let's just have something at the base level, at the base layer, that is just a cryptographic operation, as opposed to the ecosystem level operation. And obviously that comes with trade-offs. We can talk about that later. Because there's obviously, you still need to build up to support the different use cases in different ecosystems, but at the base level, it is something that is reusable.
Yeah, I think we have introduced now some of the motivation here. I think like the way I think about it too is like, I think the early cloud wallets are like, I promise all the keys are stored in like KMS, and then leave the part out where it's like, well, any server you provision can just use the KMS however you want to.
Right.
And maybe that's one step, but like the problem and the reason why this episode is called TEs all the way down is like, you really need to think about the entire path of a request as it flows through the system to actually get any benefit of doing all this like fancy storage. Because you have one rogue server, it can do whatever it wants, and like all the key security and everything you do is now useless. And so it's an interesting problem space, and something that I think when people hear the word TE, kind of they cringe a bit, because they hear like SGX fails and like all these sort of sites that like kind of document like all these different issues. So before we get into all of that, let's just take a few steps back and try to establish like some foundations of what we're talking about here and how you actually build with these these enclave environments. So first off, let's just say let's cover like what is a TE and like how do you actually deploy them today. Like I think there's SGX, there's a few different options. So I would love to hear maybe a quick explanation of like what they're actually used for and how you actually deploy them in some of these different environments.
I can try to take that, and then Zeke and or Jack, if you want to take that and add, because I think we can probably spend an hour and a half just on that, because there's so many options out there. The thing that I can talk to the most accurately is probably Nitro enclaves from AWS, which we use at Turnkey. So Nitro enclaves are basically isolated VMs that are running on AWS. And at a very, very high level, for listeners who are just like not familiar at all with what a TE might be, A TE is a place that lets you run a program in a way that's isolated from the rest of your infrastructure, right, at a very high level. And the reason why it's trusted is because there is this mechanism called the remote attestation. So generally, it is not only a place where you can run something that is isolated from the rest of the environment, it's also something that lets you run something isolated and measure it so that you can have confidence that what you think is running in that secret place or that isolated place is what you think should be running, right? And so, for example, if you are trying to run a program that generates keys and you tell AWS to run that program, it'd be really bad if you had just no introspection capabilities whatsoever and just had to trust that like what's running there is what you think should be running there, right? So that's typically what is going on with EC2 instances that people isolate in dark corners of their infra. And it's like, oh, there's this one guy, one super admin that has access to this one instance. Trust me, this is where the keys are coming from. Like that is not good security, right? So
I was going to say just like a traditional web server, but yeah, go ahead.
Yeah, exactly. Yeah. So trusted execution environments are sort of like this step up, both in terms of isolation and in terms of attestability, because you have this remote attestation mechanism. The way this works in practice, when you want to actually use these things, for AWS, you basically ask them to provision a VM. So you ask their you ask their APIs to spin up a VM with a certain number of CPUs, certain amount of memory, and then you give what's called an enclave image file that has basically everything the enclave needs to boot. And then once the enclave is booted by AWS, you can ask for remote attestation that measures what the enclave is running. And if everything goes well, the value that is measured and what you provisioned it with, there should be a match, right? And then, well, I don't know how deep you want to go into capabilities and stuff like that, but that's at a high level. I'll keep it high level for now. This is AWS. And then similar mechanisms exist for other type of TEs, where basically you're asking a computer to boot a VM in some sort of protected setting, some sort of protected world, or some sort of like attestation mode. And so that is what is happening with Intel and AMD and other types of enclaves. I'm not as familiar with the exact APIs there because we haven't really explored in detail, and we're not using them right now. That's something that's on the roadmap for us to actually span multiple types of enclaves, so we can kind of be provider agnostic and span more security domains, basically. Jack or Zeke, do you want to add anything there?
I want to introduce some point here, which is that like there's one part of it which is this like remote attestability, which is huge because like you're interacting with some service and at least via some mechanisms that this is what the code has been running, unless those mechanisms have obviously been compromised, which usually you assume that they're not. But the other thing that's really important too is like if you are an operator, you cannot actually introspect at all what's going on inside the enclave because of its isolation, which is another huge point. So like there's definitely this attestation component, but at the same time, it's like when we say isolated, it is isolated. Like
it's
only
isolated.
the application
I think there's definitely the
interface. Yeah, go ahead.
Yeah, there's definitely both the isolation. There's also the confidentiality, right? And there is the integrity guarantees, obviously, and there is also, in the case of AWS, the immutability guarantee. But when you boot something with an EIF, you know that it's going to stay the same. So the VM can't be modified after boot. So that's another big guarantee that you get.
Yeah, when I was when I was at Avalabs, we ran and still run a bridge based on Intel SGX actually, so a very different model of deployment. And so theirs is a whole different approach to this problem, where like obviously AWS has like a cloud native solution to this sort of like verifiable hypervisor construction, but there's a whole nother approach where it's like no, you should go buy a chip that has this special component in it in this case SGX, that can give you some of these properties, but you can still see it. Like I can run a server right here that's running this chip, and there's nothing I may be able to do as an operator actually to break into that chip in theory. Now, SGX has obviously had a few issues where that's not the case. But I'm curious, when people say this, like, oh, this TEs and like they have all these great properties. It's interesting to me because like you can't see it. So like, how do you know that it actually is providing these properties? Like there is some point where you do trust somebody. So I'm curious how you think about that, where it's like this magic box in the sky that has these properties, but like, how do you convince yourself that that is a sufficient model?
So, I think kind of the way I think about this is it comes down to like a root of trust, which actually, if you look at like traditional Web 2, it all comes down to root of trust. Like, how do I know when I visit google.com, it's the right IP address, right? There's some certificate authority at the top level that is signing down on sub things, and then those sub things are signing down. And that's just like X509 cert chain. So basically what you look at is, particularly with this Nitro setup, which I think was what we're most familiar with, is there's pieces of hardware, namely the Nitro security chip and the Nitro cards, that guarantee the firmware running and that guarantee resource isolation. Those are signed down from the AWS root cert. So what we do is anytime we boot up an enclave, we will get what Arnaud was talking about, like these measurements, which is the exact firmware that's running on there, the exact EIF. And in that case is like, we have built a super bare bones kernel, super bare bones logic to boot up the enclave, all around this idea of verifying it before we put in any core secrets. And we have basically is like, at a certain level, there is trust, right? Trusted execution environment. And that trust is Amazon. Probably like, if you think about it, like if Amazon got popped and they had issues, like there would be much, much bigger problems than for Turnkey. And honestly, like, even if we look at these, different blockchains and stuff running, like probably mostly on Amazon, like I could probably do like attack many networks if I could take over Amazon or compromise them. So to come back to how we do it is we attest to the enclaves as operators, and kind of the really key thing from day one at Turnkey in terms of like how this operating systems work is we, in a special air gap machine, we'd get these attestation documents that would say exactly what's running. And in our model, it actually attests to the actual application itself. It's very limited. Only one application can run. The binary that's running, the exact arguments that's going to running, like all the environment. And we take that attestation onto an offline machine where we can then do a reproducible build all independently. And after you do a reproducible build and you attest to this, then you can post a share of like a core secret that can then go into the enclave. And that core secret can be used for authorization, and it can be used for encrypting other secrets. And then you can imagine like, okay, so I can attest on this offline machine. Well, if we're comfortable with the enclaves themselves, like being, like putting these core secrets in them, then now we can write software. So one enclave can attest to another enclave, and they can actually attest to each other. And then we can do exchange of core secrets. And I think that's where you start seeing really cool properties of horizontal scalability that you just didn't see in previous generations of like this type of enclave infrastructure. And I think that's kind of like what's it's part of a big technical moat that sets Turnkey apart from how a lot of other people are approaching this problem.
So we have these TEs. They're like these sort of constructions where you can deploy some set of code and get some attestation from somebody that that's actually what's running and that it's not going to be tampered with. Now, whether it's a chip like Intel, what's signed by Intel saying that it has these properties, or signed by Amazon, at some point, this is not, this is like some sort of root trust architecture where like someone is providing this. Just like Apple gives you a chip and they say it's all good to go, it doesn't have isolation, but the Face ID or the Touch ID are all small instances of different TEs trying to perform this sort of capability. But in the case of like this sort of server style component, we have this construction. And I think the last question I want to ask here before we move into like more of the foundations is, why not use cryptography for all this? Like, why do we need some sort of TEE construction? Because I think that's usually like the constraint or like the counterpoint, at least in some applications, is to say like, oh, I have this blockchain network, and like instead of doing like really expensive MPC sort of cryptography things for, let's say, privacy, I'm just going to run a bunch of TEEs all over the place instead. Curious, like if you could maybe cover like, why we see some people use like raw cryptography, and then in other kind of use cases, they're really the only option is sort of like a TEE shortcut, we'll call it, right? Yeah, go ahead, Jack.
Yeah, I mean, I think, again, a big topic. I think the sort of like easy answer is it's just a lot simpler. Like, ultimately, when we have a TEE, we have all the infrastructure set up to be able to, deploy things pretty seamlessly into that. We're writing Rust applications. Over time, we hope to write, applications in other languages and stuff. And it's just very expressive. We can write it as if it's like, being deployed on any other web server. We don't really have limitations of having to think about using any weird, ZK VM or, writing any sort of custom cryptography ourselves. Like basically it's just very expressive, and we can, move almost as quickly as if we were running a Web 2 application stack. So that's kind of point one in my mind. Point two is it is composable with anything else, basically. So say you wanted to do some MPC construction and you were, really convinced that MPC was the right way to go for this or that blockchain application. There's no reason you couldn't like run that in a TE or have multiple different, MPC nodes, each running in a TE. Same thing's true with, any ZK technology. Like it can be this like additive thing, basically. So our feeling here was like, it's for most cases here, it's good enough. Like it's really giving us like 99% of the guarantees that we want out of anything else. In a lot of cases, we're using kind of more tried and true technologies, at least on the cryptographic side of things. Like we're typically using bulletproof, cryptographic algorithms that have been around for decades, typically, as opposed to anything super novel, which I think is really, really critical as we're thinking about pushing this technology out into the hands of hundreds of millions or billions of people. Like I really want to be using bulletproof cryptographic technology. This point is like a little less solid because Nitro itself and then a lot of the other TEE kind of stacks themselves are a little newer than some of the cryptography we're using. But I think in some ways the point stands.
Not to be confused with the cryptography bulletproofs as well.
Yes, sorry.
Yeah.
So yeah, I mean, to me, it's like, and I think you see this kind of philosophy reflected in a lot of other positions or a lot of other places in Turnkey, is we just try and take the really pragmatic approach very often. Like we're going to take the approach that we think is the sort of right risk reward trade-off to deliver the highest security product we can deliver, basically. Yeah, I don't know, Arnaud or Zeke, if you guys have anything you want to throw in there.
One thing I did want to add is like you mentioned the additive point, which I think is super important. So what we've seen some projects do, and I'll give a shout out to Succinct here actually, because they released something where they have, the ZK proof logic, which should be entirely sufficient. But, everyone is aware like these new ZK VM constructions are extraordinarily complicated. And so they have this feature they released called 2FA, which basically couples the ZK proof output with an output from like some sort of TEE construction. And so if you get a 2 of 2 that they agree, it goes through. But if you have one of the two disagree, it totally breaks down. And so that to me is like a purely additive thing. Where it's like if the ZK proof has a clear bug, like the TE is, maybe a much simpler approach is not going to catch it, or it will catch it, I should say. But then you're not putting all your trust in some sort of TE construction, which has maybe some root identity. But at some point for me, like the reason why I always have found TEs, the best you can do in some ways is that like if you're storing keys, they have to be somewhere. Like with cryptography, eventually you got to put the material somewhere. And you can't just run away from it forever. From computation, I think there's an open conversation of whether it's TEs, ZK, whatever. But from actually like storing credentials, whether those be user credentials or those be credentials used as a validator, they have to be put somewhere. So you can't really run away from this key storage problem. And if you're going to be building some sort of application or building some sort of blockchain, you're going to have to deal with some sort of notion of like key storage at some point. And whether or not you use a TE or not, is usually a decision that if you don't use some sort of more advanced cryptographic construction, you're just putting things at risk. Like if you're storing your key in memory or on disk as a validator versus storing it in HSM or TE construction, it's a big difference. Yeah, I think Zeke, you unmuted there. I'll let you cover.
I think that's a great point. That there's at a certain point, there's always some private key somewhere authorizing something, and it has to be stored somewhere. I think like what I always come back to is like, I think in the blockchain space, we always have like a fetishization with like the latest technology. I think it's because historically, like asset movement has been tied to like the technology itself instead of the utility of the technology. And I think, when I first started thinking about Turnkey at the time, 2022, I think all the solutions were like MPC. And then you start digging into it and you're like, okay, like, is anyone using these MPC solutions that are all super novel? The papers are being published as we speak. There isn't even like production grade implementations. Am I going to like trust that? And all this research is purely coming out for blockchain, or am I going to trust this technology, which is like inevitably these Web2 companies that don't talk about what they're using? Like, Apple doesn't really talk much about the HSMs they use for iCloud and stuff. Like they don't talk about that, or people don't talk about the HSMs they use for these root certs for all signing all the domain names and stuff. Like, am I going to trust these like super niche things that are very cutting edge and are like, I don't know if you've read cryptographers' code too. Like you don't really want to be using that stuff, especially when it was like just written from, I think of people here have worked at blockchain companies, like we do good code, but like it's not the most battle tested code. And I think I way rather put my reputation, my risk, and like a bunch of people's money on like a super hardened Linux kernel that is used by like parts of which are used by the whole world, and these technologies which like kind of like we talked about, even like Nitro, which is like newer. I think they came up with those chips in like 2015 or something, and those are getting massive amounts of usage, massive amounts of like positive usage, and way more than I could ever see these like novel cryptographic approaches. Same applies for like ZK VMs and stuff. Super cool work being done, but like it's just like you can't even battle test it and prove it if you wanted to and get as much usage traffic thrown at it. So I think, I take that like zoomed out view a lot.
So before we get into like more of I think like an open like kind of dialogue around like pros and cons and like kind of these constructions, let's talk about how you actually do this. Unfortunately, you can't just take your application and throw it on a TE usually. It takes a lot more thought, and like you want to do more than that. So I think to start things off, you guys have two open source things you've released, something called Quorum OS and then something called StageX, and maybe there's more tools I'm not familiar with. It'd be great to talk about what started this thing. Maybe we'll call it, like, I think you have a white paper where you released all your secrets. We can get to it later as well. But what we call like the foundations here. Before you actually build anything, there's actually a ton of pre-building you have to do that you would maybe assume exists, but it just doesn't. So would love to hear maybe to start there.
I'll start. So this is another hour-long discussion potentially, but I'll just give the high-level overview on StageX and Quorum OS. So one of the problems that you run into when you're building for an environment like Nitro Enclave is they ask you for a Enclave image file or like an EIF file, right? So how do you build that? Well, you need to figure that out. So not only do you have to build sort of like that specific format, but you also have to package your application to run in that Enclave image file in a way that that is attestable. And so one of the things that is kind of a sneaky thing that people from the outside don't really see necessarily is the fact that when you get a remote attestation, you get a set of measurements. Those measurements are hashes of contents that are, the RAM, the file system, etc. And so in order for you to reproduce, like Zeke was saying, like on an offline computer, the hash that a remote computer gives you, you have to have in place what's called reproducible builds. So if I build the software once on my offline machine and twice on my deployment machine, those two hashes should be the exact same, right? And that is just an immense rabbit hole that you need to go down. We have someone at Turnkey called Lance. Lance is just he's gone down that rabbit hole and dug at the bottom, basically. And so when we were starting Turnkey, what we did for reproducible builds was something pretty hacky and painful, which was, basically pin down all of the Debian packages we needed to build our applications, and then commit that to Git with LFS, and then have all sorts of like tooling around that to make sure that we had all the dependencies pinned exactly to the version we needed to reproduce byte for byte what was in the remote and what was on the offline machine. And that kind of led us to invent StageX, which is the distribution that is container-based. And so you get reproducible builds, not for free, but like a lot easier than you would with, I think, any other system. I mean, GUIX is like pretty usable as well, but takes a different approach. StageX is really just container native. You write a Docker file, you import your dependencies, you bring in your software, you compile it, and then you just get a reproducible build for free. So that's StageX. And then
just to pause there, right? Like people think, reproducible builds, right? I can compile my binary. The problem with the reproduction is like we're talking the whole operating system here. It's not just like your little, Rust application. It is, thousands of different components that make up the operating system.
And I would say even if it was just your little Rust application, you still have to deal with a ton of stuff that could make your Rust application binary different, right? And it's like small differences. It's small differences in like the system time can influence the binary. The user that compiles can influence the binary. The folder in which you compile. So there's like a whole bunch of stuff that you wouldn't even believe affects the binary. Like I think one of the weirdest one is the number of cores on your machine can also influence that. So there's just a whole ton of sort of normalization that you need to take care of to guarantee that byte for byte you get the same output on a offline machine versus sort of like a cloud builder or even on your local laptop that's online.
Yeah, and it's not even that like we're making sure the application's reproducible build and the operating system's reproducible build. It's that the tool chain to build all of this, like the compiler itself, has been reproducibly built. And this, like, we go down a rabbit hole here, but it's like the very first compiler to like build GCC is like built, and then that builds the rest of the GCC versions until you get to a high enough version where you can start building. The Rust compiler can start building itself, and then we don't rebuild every time. Like each step is done by like a number of people. They sign it, and then you can always go back and verify signatures. But this is like we go very deep on everything here.
Yeah, at the root of StageX is I think it's 190 bytes of like well-known assembly. That's the core, and then like Zeke said, you sort of like bootstrap up to GCC eventually. There's an intermediate thing in between GCC that you build to, which I forget what it is. I mean, it is down to the metal. It's crazy. Lance, when he was building StageX, was like going back and rebuilding all of these like totally obscure packages from like the 80s in order to just get back to like modern Rust. So it was, I mean, to say it was a Herculean effort is really an understatement. But I think, so Arnaud kind of a little bit glossed over this point, and I think it's just worth reiterating here. Like, reproducible builds in our mind is like incredibly important to running anything in TEEs. And it's the thing that almost everybody who uses TEEs glosses over entirely. So I think it's just worth kind of like reiterating why we care about this so much. When you're running something in a TE, you have, after the fact, you sort of get an EIF, let's say in the case of nitros, and you run it inside of a nitro enclave. After it's running, you do kind of have this like trust on first use thing. So say that you query it and you see it operating for a period of time, you can kind of get comfortable to say like, okay, this thing which was running before is still running now, some number of minutes or hours later. What you get from the attestation though is basically just a hash of what is running there. So, and it's a number of hashes. It's kind of like a hash of, I think, the kernel. You get a hash of the init RAM FS. So you kind of can get these like very low level primitives about what is running in the enclave. But it's a hash. You don't have a preimage to that hash. You can't really say, hey, I know that this hash actually, if we were to kind of reverse it, would turn into this particular piece of source code. So unless you have reproducible builds, you're ultimately trusting the CI pipeline that built it, or potentially a developer's machine that built it. You're trusting some single point of failure to have done the task of building that thing correctly and producing the EIF file, which ultimately gets deployed into the enclave. And so we think is like, that's not good enough. We want to remove any single points of failure in the kind of software supply chain flow here. And so basically the goal is to be able to say, I want to prove from source code that this source code is actually the thing which is running in the enclave eventually. And the only way to do that leg of source code to build artifacts, like taking a step back, when I think of the supply chain, software supply chain, you basically have developers producing commits. They use Git or some other version control software. They get it into some main branch. Then you get this main branch. You build this main branch. You produce an artifact. Then you take this artifact. Something runs it in a machine somewhere, and that's then running in production. Remote attestation is the thing that lets us go from built artifact to running in production. That leg of the supply chain we can kind of prove from remote attestation. Software review, code review is what kind of gets us comfortable with the first leg. We're producing kind of commits, a bunch of different developers producing commits, and eventually that's resulting in like a tagged commit, which is ultimately going to be released. Mm-hmm. And then that middle of like taking a piece of source code and turning it into this artifact, that is reproducible builds. And without that, the whole thing kind of just like falls apart, or just becomes this kind of trust me bro, hand wavy situation.
Because you just get basically an attestation that there's some TE running some hash, and that's pretty much it. Yeah.
Right. And like whether that's the actual thing you intended to build, or a developer, or an attacker snuck in and introduced some malicious package, or even some bug was introduced, you really don't know. So having this ultimate verification is super important for security, but ultimately in some cases, just reliability, or kind of finding bugs and stuff.
I guess one other benefit is that with the isolation, you can also enforce on the boundary like what a TE should be able to do anyway. So like it's pretty clear, like you can limit some sort of network access even if a malicious payload was introduced. But yeah, you can imagine in some signing schemes you up some of that bulletproof cryptography can introduce all sorts of issues, right? Like if you don't do the nonce properly in like a SecP signature, like you're done. So, but yeah, we'll continue to get into that. The other thing I cut you off on was the Quorum OS, which is another component as part of this, or like kind of a subsystem of StageX. Yeah, how does that fit into the story here?
Yeah, so Quorum OS, I mean, just to finish the breakdown at a high level, Quorum OS is what is part of the EIF, and it's basically part of the software that is packaged in the EIF, right? So the EIF file that you run and you give to AWS as okay, run this thing for me, please. That has two subcomponents, basically Quorum OS plus, at the end of the day, the application that you run, the application logic. And Quorum OS is our solution to the multi-party problem that arise when you try to provision an enclave with a core secret. So I think Zeke explained that a bit earlier, but basically Quorum OS is based on quorum of people, right? Operators that are declared in configuration, and then that configuration basically is a way to verify the fact that an enclave is provisioned with a core secret split amongst these operators which have the following public keys. And so basically we took a lot of care in designing this, with trying to have as much good crypto foundation as possible, trying to minimize the code, minimize the dependencies, minimize the footprint of the operating system. And it's open source, right? So you can look at tkhq/QoS, that's the repo. And over there, you'll see that there's Quorum OS, the actual operating system, which is based on Debian. There's Quorum OS, the set of libraries that applications can import and then use as part of their logic. So if you are an application in Rust wanting to sign something with a core secret, you're going to import something from QoS and then use that. If you want to encrypt something, you might also want to import our encryption crate and then use that. So basically prepackaged library utilities that you can use. And there's also the core of QoS, which is the running, provisioning state machine. So when an enclave boots, its first task is to boot and expect shares from operators that are well known. And then once that's done, the enclave is going to what we call pivot. So it goes from a phase where we're in provisioning mode to a phase where we are actually provisioned and running the application. So that transition is the core business logic that is in QoS on top of the operating system.
And that core secret there, that's like what basically the enclave uses to identify itself to other services so that they know that it is what it is, basically. Yeah. Cool. So that is like some of these core pieces. And then I think it makes sense to go shortly into like how you actually turn this into some sort of back-end system. But are there any other like important foundations to call out that you felt like were part of like a pre-build procedure to get you to a point where you could actually build something?
I think, so Zeke kind of went over this a little bit before, but the whole purpose of Quorum OS is to essentially buffer up and then ultimately buffer up shares and then ultimately reconstruct those shares into this core secret, which we call a quorum key. So we can probably just refer to it as that moving forward. And the quorum key is obviously like everything in some ways. It's used for enclave-to-enclave authentication. It's used for decrypting ciphertext and stuff inside of the enclaves. We really treat it as like the crown jewels of Turnkey. If that's lost, we are in really bad shape. And so buffering up the secret inside the enclave is one piece of it, and Quorum OS does a good job of that. But ultimately at rest, we need a way of provisioning, these enclaves with the secret. And so we had to do a bunch of work. Basically, we didn't want to have the sort of shares that go into a quorum key just be on random developers' machines. That was like just not a really we thought it was a pretty foolish thing, just considering that people are using, their machines to download random packages and do things that devs do. It's just not necessarily like a super high security environment.
Claude Code may be interested in those keys.
Yeah. And so one of the things we did early on is build out this really kind of crazy air-gapped laptop flow, so that we could, every time we were interacting with the secret or a share of the secret, in order to do a release or bring Turnkey back online if it was ever down or something, you could do that in a super isolated environment, and you could re-encrypt that secret knowing that what you were re-encrypting it to was definitely the version of the enclave that you were trying to re-encrypt it to. So that took, in some ways this is just a bunch of internal tooling, but something else that kind of came out of that was this project called AirGap OS, which technically was kind of produced for some work that Lance and I did at Polychain, but Lance kind of took it to the next level, and we produce a new version of AirGap, which is now used in kind of the turnkey provisioning flow. So yeah, in one hand, it was kind of just internal tooling and like our own deployment stack. So it wasn't necessarily like a pre-build, but there were parts of that I'd argue were kind of pre-built.
Yeah. Yeah, so you want to do your own TE platform service, prepare to implement multiple operating systems and package tool chains and everything. So, I mean, the other complexity here, right, is like, okay, when you're building out like a TE system, like you can either bind other services to it by its code hash, and so that only that code hash can interact with it, or there has to be some other thing so you can update it. And the complexity really comes when you want to support updates, which any modern application would obviously want to do. And so a lot of this quorum configuration, and I'm sure much of the complexity we'll talk about shortly, is because you need to update code. And if you bind it just to a code hash, maybe there's some very root item that is bound to a code hash, which then allows you to provision all these other services that's super thin and just like a configuration layer. But like the problem, and this is also the case for anyone using SGX and any of these other platforms, is like eventually these things have to have some sort of identity that can interact with these other services. So let's say in the AWS case, you bind it to KMS. So like only the enclave can read these keys or sign keys as a very particular example. But yeah, if you want to update that application binary, you can't just say, well, this is the code hash now, because the whole point is that you can't do that. And so then you have to introduce this like another layer of, you guys have abstracted it as this quorum key, but a way to maintain a stable identity, but still update the code that backs whatever that identity is, which you need, again, if you're going to push any changes to code. So you have to really think about the life cycle of how these things actually get deployed. And so when you're thinking about a TE, don't just think of it as like, oh, I can just code my application, slap it into TE, and then deploy it, and it's all good. It's a much deeper challenge. And it's actually surprising like how much you guys have had to build yourselves that was not provided by like providers of TEs. It seems like they kind of stop 10% of the way in and then just say like, all right, you can figure it out from here. So I've always found that interesting when I've looked at your guys' work here.
I mean, arguably we've taken it too far in some places. I think for good reason, and like there always was a reason. Like we're not a shop that just like rebuild something because we wanted to rebuild it. But I think in some cases we maybe could have moved quicker through parts of it by taking like parts of the Amazon toolchain or something.
If your key management scheme doesn't involve Faraday cages and vats of acid, I don't even know what you're doing. So so cool. We got some foundations laid here, and before we transition into actually the architecture, we haven't talked much about this like source document we're using for this conversation. So funny enough, like this all kind of started where I got deeper into what you guys were doing when Arnaud sent me a link of this white paper you guys were working on, which goes into detail how all this works. Now, some people might say like you're giving away the secret sauce by explaining how in detail all these components fit together. Because clearly, I mean, if you've listened to this podcast, half the people may be like, I have no fucking idea what's going on. Like there's so many different components and pieces and how they fit together. Other people are like, yeah, this is deep. Like this is specific. This is nuance I hadn't otherwise considered. And we'll link to this like deep white paper in the show notes as well for anyone to read in detail with all these beautiful diagrams, how all of this works. But before we go into some of the architecture, I thought it'd be great to get your guys' explanation of like, why is this document available on the internet in a way that I can read it if I wanted to go build my own TE thing? Why have you open sourced all these like really critical components that anyone starting from scratch would maybe not even think is necessary? So like, why?
Well, in order to verify the system, you have to audit the system. And that's auditing architecture, auditing source code, auditing operations. So kind of this should be table stakes. I don't know if other people in the space are doing it, but to us, it's like the most obvious. And the natural progression is all the core logic that could possibly be compromised and lead to a loss of funds eventually needs to be like open source. And we are, that's kind of a core ethos for us.
Yeah, I mean, the reason we started Turnkey was to make a verifiable key management system, right? And so if we didn't have our systems and secrets, I mean, secrets, obviously the actual user secrets are not in the open, but the way the system works is in the open. And I think it definitely should be. I think we also want to hear feedback. We also want to hear how others are approaching things, and we want to be challenged on the way we're approaching things. And if there's a better way to do it, we want to know about it. So I see it in the same way as, bug crowd style programs or security research programs. I think you benefit a ton from building in the open. And that's what we intend to do today. That's what we intend to do tomorrow. And I think the more we're going to go, the more open we should be. And so, open sourcing Quorum OS last year, publishing that white paper earlier this year, and probably open sourcing more applications, later this year or next year is going to be, just like a theme for us, basically. Trying to build more and trying to build with the rest of the community as well. So that's pretty important.
For sure. And we've gone through to just like great lengths to, I guess, make the whole system like have integrity, let's say, and we haven't even gotten into the kind of the architectural components, but like what is like we go through so much thinking about like what kind of logic and how much logic should actually sit down into the enclaves versus how much of it can sit outside of the enclaves. And we've been really consistent and taken on so much additional work than I think we necessarily would have had to bring a product to market, for instance. And the only way that we can kind of take credit for that in some ways is by open sourcing it and by talking publicly about the architecture and putting it out there. So like Arnaud said, I think we really feel like this is it's kind of table stakes the whole mission kind of. I think Arnaud alluded to this, but the eventual goal is that we're going to open source all of the enclave applications, and they should be sitting publicly, and then actually on every single request, the hope is that people can have built the enclave applications and then actually verify that their particular request was served by the version of source code that they individually compiled on their machine. That's kind of the eventual goal. And I think, we're actually closer than we're, a couple months away from probably being able to do that, which is really exciting.
Sweet. Yeah. So I think that's a great transition into what are they verifying? So now that we have this foundation to give, some sort of verifiability around like something that's running, what are the things that you actually would want to run in this architecture to do like the things that Turnkey provides, or if you're building any sort of application? So I think maybe we start off by going into how you guys have architected the system around these foundations, and then I think that'll be a great entry point into maybe some more nuanced conversation around like how to think about like these sort of architectures and how to actually run TEs in a sophisticated way, at scale. So we'll turn it over to you guys. Yeah.
Maybe I'll go super high level, and Arnaud and Zeke, you guys can kind of get into some of the nitty gritty. I think the like motivating threat model here was that for enclave source code or enclave code, we have really strong guarantees that multiple people have been involved in every deploy. Other places in the infrastructure, we don't have that same guarantee. So there are like individual people or machines within Turnkey that can, redeploy a particular container inside of that's like our, application gateway or API gateway. And so because we have these kind of two different zones, where in one zone, multiple people have to be involved, there's no unilateral upgrades. In the other zone, there can be unilateral upgrades. We took this hardline approach early on, and we said, okay, anything that we basically want to be able to say this statement, which is every single service that is outside of the enclave, everything that can be unilaterally redeployed could be compromised. And if that were the case, user funds would still be safe. So basically what that means is anything that generates keys, anything that can manipulate data associated with the user account, anything that could be used to modify that data or authorize a request from a user, anything like that has to be deployed into an enclave. And if it doesn't sort of meet that specification, then it can be deployed outside the enclave. That's kind of like the high level approach we took.
And that includes things like databases. That includes anything that's not in an enclave. Yeah.
And then just to give some concrete examples, and maybe actually let's just go through the list because that might be shorter. So like today, Turnkey has 5 different types of enclaves. The first one that obviously everybody kind of knows about is the signer, right? So the signer generates keys and signs messages. The input to the signer is a decision. So it's a decision that's like, hey, can I sign or can I not sign? That decision comes from a policy engine enclave. So that policy engine is in charge of, given a request from a user, given data with user public key registered, is that request supposed to happen, yes or no? And a third input to that policy engine is also the output of a parser. So basically that gives you the first 3 enclaves that we're running. So the signer, the policy engine, and the transaction parser. The fourth one is obviously, that input to the policy engine with the user public keys authorized. You have to have that come from somewhere trusted, right? And so the enclave that creates data and modifies data is also signing that data, so it can be persisted outside of the secure enclave, and that's called the notarizer. And then the fifth enclave that we have is called the TLS fetcher. So when we want to reach out to the outside world and connect over TLS, we do that from inside of an enclave. So basically, recapitulating, we have signer, policy engine, parser, TLS fetcher, and notarizer. And so these 5 enclave types work together to fully authenticate a request made to Turnkey. And so typically the path through our system starts with a transaction parser to parse the transaction request. Then you go to the policy engine, and then the policy engine authorizes the request based on organization data, and then that makes its way to the signer to finally sort of sign the request. And we can go through more flows, but essentially all of the components that are outside of these 5 systems are considered untrusted. So that includes things like our API gateway, for example. Like our API gateway is untrusted, and if it did modify a request, our enclaves would catch it because we actually enforce that all end user requests are signed with an asymmetric key pair. So that's an example of how we get away with having something like that untrusted, right? And similar to this sort of mode of thinking for the database, like the database being untrusted is kind of crazy, but it's not that crazy. I mean, we just signed the data out of the secure enclaves, persist that, and so if data was read back in and modified, then we would just notice that within the secure enclave code. And one thing that may be obvious from that is we are subject to denial of service, right, from outside. Like if you are modifying the API gateway, if you are deleting the database, obviously like these things are going to be outside of the secure enclave control. And so the thing that we can guarantee is that no malicious font movement is going to happen. But obviously the secure enclave is, no internet connectivity, is passive, has a key, but cannot sort of like guarantee system integrity and availability. So that may be also another topic we can dive into. So that at a high level, that's the architecture. We have that trusted zone, that's the ingress and the coordination. Or sorry, the untrusted zone, that's the ingress and coordination. And then the trusted zone with these 5 enclave types that orchestrate requests and sign messages to each other and encrypt and decrypt data. in and out.
So I'm curious just to maybe talk specifically more about the parser and the policy engine. So the parser here, like what are like people actually providing that interact with you? Because like I mean, like when I hear policy engine, like the first thing I think is like, don't sign a transaction that spends more than this much money, or like don't send it to these people. Is it stuff like that, or is it more like I've authenticated with Google and this is like my OAuth credential that's associated with this wallet? If something doesn't come from this, provisioned account via this OAuth construction, then like don't let me sign anything.
Yeah.
Could you talk more specifically about how to think about that?
Yeah. That's a good question. So policy engine is pretty flexible, and it has multiple types of rules that you can set on an organization. So the first class of rules that you can set is the ones that you kind of alluded to, which is, don't let me sign anything if it's more than 10 ETH or something, right? And so that would be facilitated by the transaction parser, where we would get the unsigned payload as input, return signed metadata as output, and that signed metadata can be something like it's going to this address, it's transferring this particular amount of Ethereum with this gas price and whatnot. And you can then write policies evaluated in the policy that metadata that's trusted because it's been evaluated inside of the context of a secure enclave. So that's the first class of policies. Then the second class of policies is authorization, like user authorization policies, where you can set constraints around who can initiate the action. So you can have on Turnkey what we call consensus policies. So for example, if you and I were on a Turnkey org, we could set something that says, hey, don't sign anything unless both Arnaud and Patrick have signed, right? And that is linked to the organization data and the concept of Arnaud as a user and the public keys under Arnaud, the concept of Patrick as a user and the public keys under Patrick, right?
So you can basically codify in that model like anything that looks like some sort of like multi-signature authority as like some sort of signature. So like typically people working with cryptography, right? It's like, okay, there's some very specific math of like how a certain signature could be generated that represents like a single identity. But in this case, like that's all virtualized into this sort of like policy engine that eventually could end with a signature. But like what actually is an input to that signature is actually much more flexible and generic than like what you may be able to get with like some sort of MPC sort of style construction.
Right. And then I think papers in this space sometimes refer to the concept of like key encumbrance, is what I've heard, is basically the concept that a key is actually not free. It's actually encumbered with a set of constraints. And so in that case, you can kind of mix and match the constraints around what kind of transaction is being signed, or the users that are acting on that.
Yeah. And my point earlier around like the buck, kind of stops somewhere, right? Like let's say that you have an MPC scheme and you have a bunch of partial key material all over the place. Where do you store the partial material? How do you determine what to sign when you have that partial material? Because like you still need some sort of policy configuration, even if it's all over the place. And if you don't, you're basically implying that like, it's strength in numbers sort of system where like, maybe we don't have any individual thing being that properly secured, but for, you need 2/3 of them to be compromised before there's some sort of reshare, and thus we should be okay. But you can still add like some sort of layer of sophistication here, which says like, even though I only have a part of the secret, I don't want to sign just anything. I want to sign like valid things for consensus, or I want to sign like valid user requests. And so at some point, you want to give more meaning to this key. And the way that you can do that these days, often the best practice is to couple it with some sort of TEE construction rather than just like a key that's hosted in KMS or something like that.
Yeah, we use this, like I think the phrase here often is like blind signing. Like you don't want the signer or whatever's operating against a key to do so blindly. And really, what that means is that you got to push some sort of authorization logic into the same security domain as the thing that's actually operating against the key.
And so you brought up this thing called the signer. And so the signer here is like obviously what actually constructs like this sort of signature. few specific questions there is like sometimes when you sign, you want some sort of randomness for some sort of schemes that can be important. And the other thing is like, so where is the key actually stored then? So is like the key in KMS? Is it like stored in some encrypted format somewhere that the enclave loads up? Curious how it actually gets that material, because my understanding is like these enclaves are stateless constructions and they like basically push stuff out, maybe with a signature around it, and then something can give it back to them. But the enclave itself doesn't actually like store anything in it. It just runs code. So curious, maybe if you could discuss either of those.
Yeah, I mean, those are both pretty crucial questions. So I guess I'll take the last one first. So the signer enclave has a quorum key like any other enclave, right? And so key material is persisted outside of the enclave, inside of the organization data. So it's encrypted and stored signed by the notarizer enclave. So anytime you create a key, our signer enclave is creating a key, and we'll come back to the randomness thing later. Then the notarizer gets that, right? And then inserts that key into the organization data. So at the end of the day, you have an organization data JSON blob. Think about it like a JSON blob with users, private keys, and so on and so forth. And then under private keys, you're going to have encrypted key material that only the signer can decrypt. So anytime you sign, what you're doing is you're taking the organization data, verifying that it's authentic, verifying it's signed, verifying it's current. We can also, just like mental note, talk about the problem of organization data being canonical or not, and we have interesting solutions around downgrade protection, but I'll park that for now. And once you have that organization data that's authentic, you extract the encrypted key material, and then the signer decrypts it, can sign with it. And you're right to point out that enclaves are stateless. The only piece of state that we basically anchor to in this setup is the quorum keys, right? So the quorum keys are this sort of like stable keys that are provisioned in enclaves, and so we can anchor to them in a way that we wouldn't be able to do if we didn't have them. So that's really the core challenge that we're solving with quorumless, and so that's why we're doing all these things around provisioning of these quorum keys and the mechanics around handling those and so on and so forth. And then on the entropy piece, the signer is a Nitro enclave, and so when you request entropy, you're actually interacting with the Nitro card driver, right? And so the Nitro card driver is then pulling entropy from the Nitro card, which is connected to the Nitro enabled server.
So the randomness is basically assumed to be part of the runtime that you're interacting with.
Yeah. And then just to add on that, one other thing that we use heavily for downgrade protection is this notion of like source of time as well, right? So the Nitro card gives us a source of current time and a source of entropy. And those two things are pretty crucial for us to know whether a copy of organization data is current or not. So segue.
Yeah, I think that's a great segue into that. You brought up a term there that we haven't talked about yet, which is this downgrade protection.
Downgrade protection, yes.
So the context I'll give here, right, is like, cool, we've signed a payload, but now that payload has a bug in it. How do we make sure that we don't go back to that and just continue to go forward on newer and newer versions of the software? This was a problem, actually, I think, in Secret Network with some SGX stuff. There was a bug in SGX that someone found a way to like exploit, and so they needed to make sure that validators were on like a certain version of like the SGX firmware to prevent like an attack, basically. And so if you just, because it still was like a valid version of the binary, so if you had an old instance of the TEE, you could decrypt all the data or something like that. And so it was a pretty sophisticated procedure, I believe, to change it. And I should probably put a note there to look back at it. I think it's still on sgx.fail. But it would be great to talk about this problem, which is to say, how do you make sure that you're on a certain version and not a version?
I think so. Yeah. So there's a couple different places where downgrade protection actually it is kind of critical in Turnkey. The one we're talking about here is sort of monotonically increasing or changing versions of org data and ensuring you're only ever operating on the canonical one. And then the other is related to key forwarding, which Zeke briefly touched on previously. But so I'll actually first talk about the kind of org data one, and then we can talk about key forwarding for a second. And I think just one critical point before diving in, Arnaud was mentioning org data, which is kind of this construct that we have, which is kind of like a grouping of all super important pieces of data associated with a Turnkey account. So this is like one JSON payload that's kind of coupled together and stored in our backend and ultimately notarized together. And the reason for that is, we don't want to have a situation where like somebody who has access to the database or potentially has access to the API server could pluck out, a piece of a key from one account and, provide it an authentication from a separate account and pass those both down into, the enclaves and basically trick the enclaves using an authentication from one account and a key from another account in order to, trick the signer into signing something that it should have been able to sign. So we kind of group, users and keys and a couple of policies all together into this one large construct called org data, which introduces a bunch of challenges because that means that if you have this single payload, that payload can't get too big. So we have sometimes challenges around kind of the total number of resources associated with a Turnkey account. And that's really just so we don't, hit too big of a size, for individual requests and stuff. But anyways, the question you're asking, Patrick, is like, okay, so say I have a Turnkey account and I'm just getting off the ground. So I create an API key. I'm at bad security practice, so I just publish the API key in a public repository in GitHub, generate a key in my account, do some dev on Turnkey. Like, okay, this is a product I want to use. I want to productionize it. And then I go ahead and lock the account down. So afterwards, I create a new API key, rotate the key I'd stored in GitHub, add some policies to further lock down my permissions, etc. How do we prevent the state of the org data at time zero, kind of right when the account was created, and a signature from the API key, which I chucked in GitHub, from being able to sign on behalf of the account in TN, so when I'd actually locked it down further. So initially we had this kind of very janky solution, which worked well for a while, and then until it stopped working at all, which was we had a concept called just refreshes. So basically every org data had a notarization associated with it, which is kind of a stamp from the notarizer that says, hey, this is valid. And we just had hard coded basically into our enclaves, like not only does this have to be a valid stamp from the notarizer, the quorum key associated with the notarizer, but it actually also has to be recent. So it has to be from within a couple hours or something. And so that just meant that on a periodic basis, we would just basically plumb every single Turnkey organization through the system and just re-sign it. Every couple hours, we just be re-signing everything. And when Turnkey was, a couple thousand accounts, that worked totally. It was fine, no issues whatsoever. And then we started to get to a size where, plumbing millions and millions of accounts through the enclaves every couple hours just was, absolutely taking down everything. And so I don't know, Arnaud, if you want to go into details on where we've kind of landed now, but it's a pretty clever solution that I think's kind of cool and probably has valuable, or it's a valuable architecture probably elsewhere in crypto, I think.
Yeah, I mean, basically the idea is simply using a Merkle tree and a Merkle root, right? So each organization is part of a tree, and then that tree rolls up to a root, and then that root is sort of your proof of inclusion and proof of currency as well. And so when an organization is notarized for the first time, it's included in the tree, produces a new root, and then that root is the thing that is being refreshed, as opposed to each organization within that tree being refreshed independently. And so that leads to a system where if you don't change your organization, which is by far the majority of organizations at Turnkey. By far, organizations don't switch their users or their authenticators or whatever all that often. If you don't have any of these modifications that produce a byte change in your organization data, you don't need to be refreshed, right? You're kind of included in the refresh of the roots only if you add a policy or remove a policy, add a user, remove a key, something like that. Then you have to sort of change your inclusion point on the tree, and then that will trigger a new root. So that is really kind of the main change that we made, is going from a system that refreshed all organizations, regardless of what they do, every X hours, to refreshing only the organizations that need to be refreshed when they do update. And so that was a pretty massive change that we rolled out.
That was so fun. Hopefully it didn't end up as an incident to figure out how to do that.
No, I mean, it did actually. Yeah, there was a bunch of pressure on that database, because you can imagine like refreshing all these organizations. It's not only enclaves processing, but it's also database writes, right? Because you're refreshing and producing a new signature, so you need to persist that signature, and so it just let database loads. And so I don't know, you've been there, you know how it goes. At some point the system saturates in terms of CPU memory, and so yeah, it
unless
wasn't
unless it's serverless. No, okay.
Yeah, I mean, yeah. But yeah, I mean, the thing that happened is basically we were getting closer and closer to our limits in terms of CPU utilization, and so that became quickly something that we were very scared of, and we had to move quickly.
Yeah.
But luckily, no big, halting of the system or anything like that.
So I'm curious, like, so you said like when an organization changes, does it like does the change have to then go through the enclave that then generates like a new root basically from that or something like that? Or because I'm assuming the other way, and then the state machine only moves forward, I guess, in terms of like what can, and then that is what actually has the time. Got it. Cool.
That's right. Yeah.
Yeah, when you say TEs everywhere, it's really all the way down into the system. Yeah. And then obviously I'm assuming like the organization here, the users you're referring to are not like keys provisioned, but it's like the organization managers that can make like some sort of configuration change to like what the policy engine is or something like that.
Yeah. So if you are on an org, it would be like the public key that you registered under your user to represent you in your organization. Yeah, I mean, I'm thinking also we kind of glossed over the other downgrade protection, which is kind of the application level, like when we deploy into secure enclaves, how do we update stuff? So Zeke, do you want to talk about like key forwarding and key OS manifest and nonces? I think that'd be interesting.
Yeah. So I guess this is basically like diving deeper into QoS and kind of like the abstractions we've created there. So we have this thing called like the QoS manifest, which describes every aspect of what's running in the enclave and is part of like what we verify. And it's also part of what we have, we call it the manifest set. So these are the people who are signing over the manifest and basically saying they approve of like the configuration. And then separately from that, we have what we call like the share set. And those are people who hold like these Shamir shares. So basically, if I'm an enclave and I'm going to do key forwarding, kind of the most natural to understand case is I get an attestation document that has the hash of the manifest and all the signatures over the manifest. So I can see, okay, like a certain threshold of the manifest set has approved this manifest, and it's the exact same manifest. And I can also see in that manifest is like what we talked about, these measurements of what's running. And I can see in the attestation document, the manifest matches those measurements. So I know that enclave is running the exact same thing as me. And importantly, it's like in the same AWS account, which is a small detail that has very big implications. So what I can then do is like, what we actually do is like in the attestation document, we embed what we call an ephemeral key. So that's just a key that's only ever generated in the enclave, never leaves the enclave. And it's kind of used to ID that exact instance. So what we do is we encrypt the quorum key to the ephemeral key the other enclave, and that way we can at least enclaves with the same version can share the quorum key with each other. So we kind of quickly run into this thing if you're running that, and every time you need to upgrade, you need a bunch of developers to go do this really laborious process of what we call a boot standard. And that's where we talked about you get out your air gap machine, you do all these reproducible builds. Like it's like literally it could be over a day, right? If you do any hiccup, you got to restart the release and stuff. And get kind of these key shares on the air gap machine and getting the key shares back online. So what we can do is like we can move the operational complexity down to just approving manifests and having the same manifest set and say, oh, if this threshold of the manifest set has approved this new version of the application, I am willing to share my key. And there's also, we use like a nonce to predict, like basically like it's up to the manifest set to like make sure, okay, I'm only signing incremental nonces. Because otherwise it's like these hashes can change and there's no way of being like, oh, this is the newer hash, right? At a certain level, it's always a social coordination problem. So basically this manifest set will update the manifests for the same application, and a lot of like social constructs in here, but like you still get your aggregate machine, you still do the reproducible build, but you don't do any of this attesting to the enclave or share. Basically what you do is you put that manifest, the enclave boots, and Arnaud was talking about the state machine. So the enclave's in the state machine where it's waiting for the quorum key. And what we do is we have that enclave will say, hey, here's my attestation document, which includes, you know, all the measurements, the manifests, and here's the manifest. And I'm going to send it to an older version of the application that has a lower nonce. And then that is going to do all the attestation. And on top of that, check that it has a newer nonce and the threshold of the manifest set. And then it will do the key forward again by encrypting the ephemeral key. Yeah, so that's like kind of like how we do upgrades at the application level.
So this stops, like, say that we had, we need the key forwarding because operationally it's just like so much easier for us to do a release, you know, with key forwarding and stuff. And the nonce thing here, really what it's doing is, say that we had version 1 of Turnkey's enclave, and then we moved to version 2, and then you know, we moved to version 3, and then we realized that version 1 had an issue in it. Like version 1 had a security vulnerability or something. We don't want someone to be able to spin up a version of you know, signer version 1 and have version 3 key forward to signer version 1, which could then be, you know, exploited. So the nonce here kind of enforces this like linearity of enclave releases. So we're never like going backwards.
Yeah, it sounds there's a lot going on here in terms of different pieces and making sure. I mean, I think it's interesting when you think about the leap that it takes to go to like kind of this sort of level of secure environment, and it's definitely not for the faint of heart. Like if I think like the one thing I want to get through to people is, even though it can kind of seem like, oh, you can just have some sort of like TE running, it's more than that. Especially if you want to be able to update the code and you want to make sure that no other part of your infrastructure can just unilaterally perform some sort of action, because then at that point, none of it was worth it to begin with. And so I think there's sometimes a misnomer here where it's like, oh, if there's a TE part of the story, it means I'm safe, or that if a user interacts with some service, that it's safe. But yeah, I mean, if your server can just YOLO trigger the TE, you're not safe. And the TE didn't add anything other than maybe being able to just take the raw key out. And that's pretty much it. So yeah, I think that there's a level of, you know, increased complexity here as you think about actually trying to secure an environment that has all these pieces working together, especially if you're offering it as a platform for other people to interact with, because it, you know, multiplies the complexity here quite a bit. So yeah, this is really cool. I'm really glad that we were able to get to this level of depth on this sort of construction. And yeah, I mean, the work you guys have done is crazy. I think when Arnaud shared the original white paper, I was like, I think my first comment was like, you actually did the thing, which was like going all the way down to the bedrock and like figuring out how to actually get all these things interacting together without actually opening up one of these shortcuts where it's like, yeah, it's all good, except for if this one thing doesn't happen. And you've really based it on this like root of trust principle throughout the whole system, which is super cool to see. So very cool, very, very nice to see you guys take it so seriously and go through in detail how this all fits together. I think you mentioned a few times there's a few hour-long topics sprinkled in here, which I would love to continue going into, but we're starting to run up on time here. And so I would love to, turn it over to you guys to talk a little bit more about what you guys have planned here for like how you think about the trajectory of what Turnkey is doing and like the types of things people are doing with it. Because, you had a great spoiler at the beginning that like conceivably anything that manages keys at scale, like these are problems you need to solve. And so, it'd be great to hear, what people are using Turnkey for today. And then is that just more of what you want to see going forward, or are there whole new ways to interact with this sort of infrastructure?
I guess there's a lot. I think the cool thing we're kind of in this like almost paradox of choice moment at Turnkey, where like we started from something so low level and it's so complicated and stuff. And I think now that we're at that position, there's actually like incredibly like a million different directions for us to go, which is great, but it's also tricky to like prioritize it. I think the thing that, there's tons of different, we could get into all the different kinds of applications that are being built on Turnkey. And I think one of the really cool things is that it's really not that concentrated, which is cool. And like, from like a business startup point of view, one of the things that gives me a lot of confidence is it's not like all of our revenue is tied up in like one specific kind of customer or another. It's really like a very wide range of companies building on top of Turnkey, which is great. I also think that speaks to the original decisions we made and kind of making the choices around very flexible primitives. It just means that it's composable and can kind of work with a bunch of different new kind of crypto companies as new verticals arise, or as new kinds of ideas come into the space. So that's very, very cool. So we definitely hope to see a bunch more experimentation, a bunch more iteration by customers. I think also a bunch more experimentation, iteration on kind of the core things that we're building in Turnkey. So this is like more kinds of transactions we can parse, more kinds of policies, and sort of expansion of our policy language. Definitely we're trying to push Turnkey, the system, to the limit. So thinking about scalability and performance a lot these days. It's like a very important thing. So like we're working on multi-region deployments of Turnkey right now to bring latency down across the board. I think that's all sort of like obvious under the bullseye sort of stuff for us. The thing I think Arnaud and Zeke should maybe talk about a bit, which is maybe a less obvious usage of Turnkey, is what we're calling the Turnkey verifiable cloud. And I think that's a lot of the, I guess, excitement and sort of energy that we're pouring in right now is kind of around TBC, as we're saying it. It's been a long time. There's a lot of iteration and discussion about what acronym we wanted, and we finally landed on TBC, not going back on it. So Arnaud, you want to talk through that a bit?
Yeah, I mean, the idea is pretty simple, right? Like, as evidenced by this discussion, which was full of rabbit holes and very complex, there's a lot to deploying stuff in TEs. And so the idea with Turnkey Verifiable Cloud is simply that we are going to offer the ability for someone to deploy their own workload on top of our infrastructure, right? So the use cases there are not limited to key management or operations that require a wallet or a private key, but it could just be pure functions or sort of like programs that you want to run that are not really crypto related at all, right? Like could be something that processes PII in a trusted way, or you can run a VPN node in a way that is attested and trusted. Or I also see people wanting to run blockchain nodes in a way that guarantees that it doesn't leak queries or doesn't log their data in some way. There's also a lot of talk about verifiable transaction parsing as a service, right? To kind of expose metadata in a way that's trusted to wallet UIs and users. And just like more broadly, I think verifiable computing is probably a primitive that is going to be leveraged in the future. So yeah, I think it's just something that we want to do to make sure that our foundations are not kept inside of Turnkey just to deploy our own stuff, right? It can be useful to a lot of other builders in the space. So yeah, pretty excited to see where it goes.
Yeah, and I guess since like this podcast has blockchain roots, like to tie it back, I've been working in the blockchain space my whole career, and the way I think about it is there's different ways to have verifiable compute. I think we touched on this in the beginning. I think most blockchain people, like, the first thing that comes to mind is consensus. You see ZK VM, and I think TE is the other thing here. And blockchains, they're very specific, right? They're like a state machine. You also have like ordering of operations to the state machine. But I think kind of like the thing I've been saying for like many years now is like, we're going to see a spectrum of applications and the spectrum of needs from the technology stack. And I think the way I think about it is there's an extreme end of that spectrum of kind of like blockchain technology as we know today, and kind of like what people were, really into in like 2020, like this Ethereum like thing where it's a state machine, everyone can verify the state transitions. That'll probably move to like ZK VM verification, and then there'll be some consensus on the ordering of the state transitions. But you can think like, okay, hey, like I don't need, if I'm building, I don't know if the next FTX is a great example, but like I'm building something where it's like, okay, I'm not guaranteeing censorship resistance. I don't need to have everyone re-execute. And maybe latency is really important. Maybe microservice architecture is really important. Maybe I want something that looks a lot more Web 2 to service this application. And maybe part of the product is more providing verifiability, maybe providing some transparency, maybe secret compute, right? There's like a lot of different things you can do with TEs. And I think it kind of like relates really well to what you're doing with Commonware, right? Like we are going to see infrastructure kind of build vertically for applications, right? And that's like what you do at a Web 2 company. You don't talk about what infrastructure you're building, right? And you don't like just build these like super generic, like, run times that are like really slow and blah, blah. Like you build things that are like to whatever your needs, your set of trade-offs is. And I think the way I think about it is like TEs fit into like a lot of different areas there. And kind of with Turnkey Verifiable Cloud, like I think it's like very, TBD into what direction is going to be going. Like we're going to be iterating to try and find certain areas of product market fit, but this is a very low level platform, and kind of the platform we have built Turnkey on, right? Like there's a lot of operational complexity here. And I think probably what's going to happen is like we will expose varying amounts of that operational complexity depending on like how much control you want in the process. But I think like, I don't know, to kind of give an example of like where TEs are like really interesting is like non-deterministic compute, right? Verification of TLS termination. We could talk about, this might be a rabbit hole that I don't want to go down, but like AI models that cannot be deterministic, asynchronous execution. And then there's like things like more privacy things like, health data. You already see stuff built around this, or like, user data that needs to be private and operated on. But basically, I think it's a very wide thing. And I think kind of the point I want to hammer home is just like, we're going to see a proliferation in kind of what looks a lot like blockchains, right? We talk about Merkle roots instead of blocks where we have timestamps. Like we're going to see that, and we're going to see it built for application specific as kind of these type of patterns get more like less niche, and we see the space mature from technology, like the technological aspect.
Yeah, I mean, I think I always think about it as this trade-off between like what is your efficiency target and then like what is your security target, and often those are a slider you can choose. It's very rare that you can get max efficiency and then also like max security in whatever context you're referring to it. And it's interesting to me as TEs often are represented as like one end of that spectrum, which is like still interesting security properties, but like you can't do more efficient than what a TE kind of does in a lot of these contexts, especially private computation. It's extremely slow. I was playing around with some ZK VMs actually like a few weeks ago I was playing around with like some time lock encryption stuff and was going to use like a ZK VM to like verify that the encryption was actually done correctly or something like that. So that when you binded the TLE, that you knew it was going to be decryptable, which is kind of an interesting and nice property. Yeah, not plausible. Like I ran that locally on my computer and I think I gave up because it was like 10 minutes in and still no dice. So, I mean, I think that a lot of these cryptographic things are really interesting, but oftentimes like you need to ship something. And so it'll be interesting to see at some point whether or not we see a convergence of the two where like this cryptography gets so fast that it's useful. I think historically that has not been anything close to the case, and that like just running stuff in like kind of an interesting environment like this is dramatically faster and cheaper. So it'll be interesting to see.
Yeah, another rabbit hole, but I think the conversion, these ZK VMs are executing RISC-V code, and unless you're executing that on native hardware, like you're never going to get native speeds. So even if you want to use a ZK VM, you can do the optimistic execution with some native thing, whether it's like transpiled or whatever. But you could do that in TE, right? And then you get better guarantees on the optimistic execution. So like we're talking about like layering security models as well.
Yeah, I think Flashbots has explored a lot around like, using TEs for almost everything here. And like, yeah, they're, today and who knows how long, I'm sure a while, like there's very interesting things that don't really fit in one bucket or the other, where like, yeah, using this is a really interesting approach to the problem that is just strictly better than not using it. So yeah, it'll be interesting to see. Yeah, but yeah, thank you all for coming on and taking the time here. Really interesting conversation. And yeah, for people that are looking at TEs, like don't just think running a TE is running a TE. You got to think about the full life cycle of what you're actually attesting to and what you're actually running. And fortunately, the folks here at Turnkey have released some open stuff that may be useful for you. But if not, you know where to find them. So.
Awesome. Thanks, Patrick.
Yeah, thank you.
Yeah, thanks.
Bye.
I'll end the recording here.